Okay, so we left off on Wednesday. We wrapped up our talk of gradient descent. Okay, steepest descent. Yeah, question?
So no online for today?
Oh yeah, I forgot about that. Okay, sure, we'll do that. We'll do that. Okay, so we left off talking about gradient descent. Oops. This is 102B, week 2, Friday. Okay. Okay, as a way to minimize a function. And so we use that to minimize the least squares loss function, right? Okay, so far we have minimized the least squares loss function. For linear regression. I feel like really loud. Okay. So I want to show an example of us using gradient descent to minimize a different loss function in a different context. Okay. So I will show you another use. Well, gradient descent is very useful, but this is just another use or application for using gradient descent. Okay, and so this is it's kind of a fun one, and it's beyond the scope of this textbook. I'll point you to some resources, and I'm hoping what I give you guys will also be neat. Okay, so there's been a lot of hubbub about neural networks. Okay, and so here I'll just give you kind of maybe the simplest form of a neural network. Okay, so we will look at what we call an artificial neural network. Okay. And the idea is, it's based on the idea that in our brain we have these neurons that are all interconnected in this crazy network of patterns, and one neuron sends signals to another neuron or a few neurons, and then those are connected and they receive signals and they send other signals, right? And somehow in our brain we have all of these neurons connected, just sending signals to each other, and somehow we are cognizant and able to think and process and all of this, right? And so as far as in this field of computer science, machine learning, statistics, all of that, we've created these things, and we can take inputs and produce outputs, and some of these applications are computer vision, and so we'll do like the very most basic form of this, okay? And so as far as a neural network goes, I'm going to use this is based off of there's a series of videos on YouTube, okay, by Welch Labs YouTube series. Okay, this is where I'm getting these examples here. Okay, so we're going to take our inputs, and I will create our inputs X, and then our output will be Y. Okay, and in our most simple example, our inputs will be the hours of sleep that a student gets, and the hours of study, and then the output will be the score on the exam, okay? And so, just for our training data, okay, we'll have 3 sets of data, okay? So one time the student slept only 3 hours, studied 5 hours, scored 75. Another time the student slept 5 hours, studied only 1 hour, and scored 82. And then another time they slept 10 hours, studied 2 hours, and scored a 93. Okay, this is what we call our training data. Okay, we will use this data to quote for our neural network to learn. Okay, so we use this data to quote train our network. And then we'll have, kind of a test case. And the test case says, okay, let's say we sleep 8 hours and we study 3 hours, okay? And then we want to know, what are we going to get? Okay. So the way our neural network looks is that, we're going to have 2 input nodes. This is what we call our input layer. Okay, this is our input layer. We have, because our x, there are 2 x values, okay? This will be, one of them will be hours of sleep, and then the other input will be hours of study. So we can call this x1 and we can call this x2. And then in our output, this is our output. This will be the score. This is our y. Okay. And between here and here is our network. And so there is, we have something called a hidden layer. And in the most basic neural network, you have, which is what we're going to do here, is one hidden layer. And maybe I'll use some different colors. Okay, and so each neuron or node connects to each of the nodes in the hidden layer, and then we're going to take the outputs in each of these, feed in here, and produce our output. Okay, so this is how this is what it looks like. And then you have, I don't know if you've heard of things like deep learning, okay? Deep learning, basically you have your inputs and then you might have like several layers of hidden layers, okay? And they all kind of interconnect. Okay, and so, this is the deep part, okay? You have multiple hidden layers, okay? But we're not going to bother with that, okay? We're just going to keep it simple. But the idea can be expanded. Yeah?
What do you mean by hidden layer? Is it just something we can't access?
This is just the terminology that we use. What we mean by hidden is like it's not like we haven't recorded measurements for it. Okay, we're just taking our inputs and we have our outputs. So what we're looking at is the input layer and our output layer. Okay, and then there's something called the hidden layer, and this is just kind of setting up how the neurons interact with each other. Okay, and let me just kind of explain the way the network works. Okay, so I'm going to just go ahead and copy this onto the next slide. Obviously, you don't need to copy it. Okay, and so the way it works is, you know, each arrow that we have here carries a weight. Okay. And so these inputs, the inputs get weighted as they travel to the next layer. Okay, the inputs to the you know, next layer. And so right here, what we're going to get at this node, which, you know, we can call Z or whatever. Okay, so if we call our hidden layer Z, at this node, we're getting a weighted value of x1 and a weighted value of x2. Okay, so at Z, there, you know, we're getting something that gets weighted there. All right, and then at the hidden layer, okay, we apply a function to our inputs that produces another value. Okay. Okay, that function is called the activation function. Okay, and so you know, basically if we just took a look at one of these nodes, right here, I'm going to just copy this. Okay. So this is, you know, x1 being multiplied by some weight, okay, which I'm going to call weight 1, 1, this, okay, this is z1. And then over here we have x2, and this is being multiplied by a weight, weight going from 2 to 1 in weight layer 1. Okay, so this, when I have 2, 1, this is from node 2 to node 1 in the first weight matrix. Okay, so we're going to have, basically, at Z, the, you know, the value that we have at Z in is going to be, you have x1 times weight 1, 1, 1 plus x2 times weight 1, 2 at 1. Okay, so this is what gets sent over here, and then we apply a function to this. Okay, so we apply a function here. We just say, you know, function of this thing, and we get you know, some output there. I'm going to say A. Okay, and so each of these are going to produce a value there, and then those get weighted further. Okay, so the output, the input comes out here, the output comes out A, and then we're going to apply a weight here. Okay, this is going to be weight going from here 1 to 1 in the second weight matrix. Okay, so inputs that produce another value. Okay, those outputs get weighted again, at the next layer. Okay, and they travel to the next node. Okay, and those weighted outputs get combined at the next node. Okay, and so we'll have the outputs come out here, and so at this node Y, what are we going to have? We're going to have A right here being weighted combined with this output A. So if I call this Z1, Z2, and Z3, and we say after we apply the function, after applying the function to this stuff and we get A, we would have A2 weighted, and we would have A3 also weighted. Okay. And these all come together right here. Okay. And then lastly, so we can just call this Z2, or Z at our, maybe this is kind of our second layer, so we can call this our Z second layer, and then this we'll say is our third layer. If we combine all three of these and we get Z3, and then we finally apply another function here to get our output. Apply the activation function again. And to get our output. Oops. Okay, is that okay? All right, so let me kind of put this in some matrix notation here to just kind of see where we're going. All right, so let me, oops, rats. Let me get this. Okay, so we have our input matrix X. Okay, so if we think about what X is, so if we just scroll back, our X, we can treat our X's as this 3x2 matrix. Okay. X will be our 3x2 matrix right here. And you just kind of scooch this in a little bit. We have 3 training cases. And we have 2 X variables. And we will multiply this by our weight matrix W. So our first weight matrix which we will call W1. Okay, our first matrix W, if we look at all of the arrows that we have 6 arrows, right? And we have we have the ones that apply, we have 3 coming off the x1, and we have 3 coming out of x2. So if we look at this, our weight matrix is going to be 2. Let's see, 2 by 3, to indicate that we have the weight from node 1 going to the first node in the hidden layer, weight from the first node to the second node, and weight going from 1 to 3. Then we have weight going from 2 to 1, the weight going from 2 to 2, and the weight going from 2 to 3. Okay, this is a 2 by 3. We have 2 input variables, or I should say 2 input nodes, and 3 output nodes in the hidden layer, right? So at this point we can say, we can multiply x times W okay, and what is the resulting dimensionality of Z? It's going to be 3 by 3, right? So the Z at our second layer, so we'll call this Z at the second layer. So this is kind of our inputs at the second layer. This is going to be a 3 by 3 matrix. Okay. This 3, why do we have 3? This 3 represents our 3 training cases. And this 3 represents the 3 nodes at the hidden layer. Okay, so our training data, x1 and x2, has been turned into kind of inputs at the hidden layer there. And so we will apply a function f, okay, apply f to z, okay, and then the output there remains 3 by 3. Okay, so we're just going to apply the function element-wise to our 3 by 3 matrix Z2. Okay, and so this is going to be our A2 matrix. Or let me, I apologize. In wait, let me. I'm afraid I made a mistake somewhere along the way, but okay. So in the video, just to remain consistent, they use a lowercase a for whatever reason. Okay. Okay, and then let's keep going here. So now we're going to apply a weight matrix here. What is our second weight matrix? So the output of the hidden layer is A2, which is a 3 by 3 matrix. Let me just make sure. Okay, so we're going to take our outputs. The outputs here, we have A2. This is a 3 by 3 matrix, okay? And then we're going to multiply that by our second weight matrix. Okay, what is the dimensions of the second weight matrix?
3 by 1.
So W2, yeah, we've got three coming in and 1 going out, right? So we go in and we're going to have W basically 1, 1, W2, 1, and W3, 1. So because we have three coming in, 3 nodes in, and 1 node out. So this is going to be 3 by 1, exactly. Okay, and so after we multiply A2 by W2, this is going to give us how many dimensions here? 3 by 1, right? And we can call this Z, because it's going to be the inputs at our third layer. So we're going to call this Z3. Okay, so at Z3, we have a 3 by 1. Okay, so this is our Z3 matrix, okay? To indicate that we have, these are our 3 test cases. The 3 here is our 3 test cases, and kind of the one, kind of the output. And then lastly, we apply our function to Z3, and this will give us our predictions, our y hat. Okay, and so we will have, this is going to be a 3 by 1 matrix to represent the 3 predictions that we make for each, or the prediction that we make for each test cases, right? We're going to have 3 test cases, each one gets a prediction. Okay, so, sorry, I know I'm all over the place as far as this goes. So the way it works is we start with our X matrix, and we multiply it by our first weight matrix, and that's going to serve as our Z's, our inputs at the second layer. We apply the function, our activation function, at the second layer, and this will produce the kind of the outputs of the second layer. We multiply those outputs times the weights of the second weight matrix, and this will provide the inputs at our third layer. And lastly, we apply the function at our third layer, and this is going to produce our predictions y hat. So this is what's going on in this simple neural network here. I just want to make sure everyone is okay so far. Okay, so I'm just showing, all we're doing is we're just taking these inputs, we're just multiplying them by some weights, and then we apply a function, take those outputs, multiply them by some more weights, and then we apply a function. Okay. And the amazing thing is that you just shift the weights around, and you'll get this very powerful way to make good predictions. Okay, so let's see. I'm wondering if I should bother with the code now or later. You know what? I think we'll keep going here. Okay, and then we'll start looking at the code on Monday. Yeah, question.
So this is, I guess, if you were just to talk about Propagation, would this be 3 hidden layers then?
No, there's only one hidden layer, but there's 3 nodes at the hidden layer, okay? And so those 3 nodes appear when in our first weight matrix. It's 2 inputs, and then there's 3. It's a 2 by 3 because we're taking 2 input values, but then we're sending them to 3 nodes in the hidden layer, okay? And then when we go from the hidden layer to the output layer, it's going 3 by 1 because we're taking the 3 values from the hidden layer and we're combining them to just 1 value in the output layer. I know it's a lot. And okay, so anyway, this is what we do, and kind of, you know, all we have to really do is we just figure out the weights in this matrix. Okay, there's 6 weights to figure out here, and then there's 3 weights to figure out here. That's really all we have to figure out, and then when we figure those out, we have the ability to start making some predictions. Okay, and as far as figuring out the weights, we can use just the plain old difference, you know, sum of squared residuals as far as our loss function goes. Okay, so we can treat our to train our network, quote, all we have to do is figure out the weights in the 2 weight matrices. W1, a 2 by 3 matrix, and W2, which is a 3 by 1 matrix. So we just have 9 weights to figure out, okay? So we have 9 weights to figure out, and we want to figure out those weights with respect to the loss function, right? So we're going to define our loss function as a way to, you know, to measure how good our fits are.
Miles,
Yeah.
how about the 2F function, the F function?
Okay. Yeah. I'll mention those in a second. Okay. To measure how good our fits are. Okay. So we can. Yeah. I'm sorry. Let me backtrack and talk about the activation functions. Okay. And so there's all sorts of there are options that we can use for activation functions. And one of the activation functions that's most commonly used is known as the sigmoid activation function. Okay, so sorry, let me backtrack. Okay, so the activation functions, the Fs. These are the Fs. Okay, so basically. We have a choice. Okay, when we set up our network, we can choose what these functions are. Okay, we can often choose which function to use. And I would say a common choice is the sigmoid activation function. And what the sigmoid looks like is it goes from 0 to 1, And it looks like, I can't, why am I having such a hard time drawing this curve? It looks like this. I hate this, all right. Let me show you. That's not. Wikipedia will have a better picture. Okay, it looks like this. How do I copy this? Can I copy this? Copy image. Okay. I love computers. All right. Oh no, that's not right. Okay. Well, it looks like this. All right, and basically it's just 1 over 1 plus e to the, I guess, negative t here. You just take the input, and so the inputs go from anywhere from negative infinity to positive infinity, and it just puts it on a scale from, it reduces it to 0 to 1, okay? And basically, if you're close to 0, you're going to have, it's going to be 0.5, or if you're at 0, it's 0.5, and then as you go higher or lower, it goes from 0 to 1, okay? So it goes from 0 to 1, and it, at 0, it's 0.5. So this is just 1 over 1 plus e to the, e to the negative t, okay? This is the sigmoid function. Okay, but it looks, can't I? Why did this not copy? I'll just, snipping tool. Snipping tool is my other friend. Okay, here we go. There we are. All right, that looks much better. Okay, ta-da. All right. Okay, so that's what we use, okay? And then our loss function, squared residuals, generally what we can use, okay? So again, there's an assortment of loss functions that we can use, but because of the convex nature of a squared residual function, we often like to use that, okay? So loss function to measure how good fits are, so we will use a squared residual function. All right, and so we will say our loss is going to be the difference between basically what our actual value is minus our y hat squared, and then we'll sum these up, okay? Oops. And we can multiply this by a constant 1 over n or 1 over 2 or whatever we want. I think in the video they choose to multiply this by 1/2 just to simplify things later, but effectively it's just the squared residual summed up, okay? And just keep in mind, what is our y hat? If we flip to the previous page, how did we get to y hat? Y hat is we applied this sigmoid here, and then this is the product of all of this, and then we applied the sigmoid here, and this is the product of that, right? So we could, we can rewrite y hat to be, a bunch of nested functions also. If need be. Okay, so once we have our loss function, how do we go about applying gradient descent to train our weight matrices? It's the same exact problem that we did for least squares, right? Least squares regression, we had a loss function, and then we wanted to train, or in other words, we wanted to find the w's that minimize the loss function. Same thing here. We have this loss function, and we want to find the w1s and w2 that minimize this loss function. Okay. So to train our network, we will try to minimize the loss function, okay, by changing the values in W1 and W2. Does that make sense? Okay, and so how does gradient descent work? So gradient descent, the idea behind gradient descent is we're going to calculate the gradient of our loss, okay, with respect to basically W1 and W2. Okay, and so in order to do that, we're gonna, I don't know how far we're gonna get. Okay, we got to find kind of the gradient with respect to, you know, each of these weight matrices. Okay, or we're gonna find basically the derivative with respect to these weight matrices. Okay, and this is kind of what's known as back propagation. I guess I should, if you want to flip back in your notes, all of this going forward, this was known as forward propagation. Okay, so back propagation, you know, people say this is like the most complex aspect in training a neural network, and they're probably right, but the idea behind back propagation is not too crazy complicated. Okay, it's effectively you want to take the derivative of your loss function. Okay, but whenever you take the derivative of something and it's like, you know, a function within a function, which is kind of what we have here, what do you have to do? Chain rule, right? Okay, and that's what back propagation is. Okay, you're taking the derivative with respect to something. You see, oh, it's kind of nested in something else, so you apply the chain rule, and you get, you know, the derivative of the next thing, and then, you know, if that itself is a product or a function of something else, you apply the chain rule there until you get all the way to the end, and there's no more chains left to do. Okay, so back propagation is effectively just we want to take the derivative of the loss function, okay? Of the loss function, and when we need to, we will apply the chain rule. Well, I guess if you want to try it out, you can try it out. Okay, we'll do it on Monday. We'll go through and we'll take the derivative of all of this stuff on Monday, and we'll see kind of back propagation. We'll see this thing, this neural network being applied, and then we can see some cool applications with it. Okay, I think we'll have fun with this thing. Well, I'm hoping. I had fun with it, so maybe you will. Okay. Have a good weekend. We'll see you guys on Monday. Stay safe as you if you have to do any driving in the rain, especially. And we'll see you in a couple days.